Hello friends, today's question. A rectangular, rigid fixed block has a long horizontal edge. A solid homogeneous cylinder of radius r is placed horizontally at rest with its length parallel to the edge such that the axis of the cylinder and the edge of the block are in the same vertical plane as in figure. There is sufficient friction present at the edge so that a very small displacement causes the cylinder to roll off the edge without slipping. Determine, so we have four things to be found out. The angle theta c through which the cylinder rotates before it leaves contact with the edge. B. The speed of the center of mass of the cylinder before leaving contact with the edge, and the ratio of the translational to rotational kinetic energies of the cylinder when its center of mass is in horizontal line of the edge. So this is the figure. So we have block. On the block we have given a cylinder, and this cylinder is going to roll off this edge, and we have to calculate all these three things based on that rolling without any slipping. So we can draw a much simpler figure for this little complicated one. You can see that this is that basically block, and cylinder is just about the edge. So this is a cylinder, and at this particular moment the radius, or we can say that mg, is directly at the edge of the block. So this is our r, and then it says that it rolls over this edge, and we have to find out this angle theta c. So let us denote. Now we have the cylinder which is about to roll off this edge, and this is our radius, and let us suppose this is our theta. So we can find out that this will be equal to r cos of theta. So it is rolling in this direction, and finally we are going to find out when its center of mass is in the horizontal line of the edge. So we can now the center of mass is in the horizontal line of the edge. So this is the horizontal line of the edge. Now the center of mass is the horizontal line of the edge, and it is rolling in this direction with the omega, let us suppose. So this is much easier to understand now. First of all, from this figure we can say when the edge is at this particular position, at the rest on the edge, so at this the potential energy of the center of mass will be maximum, and at this moment it is stationary, so its kinetic energy will be equal to 0. Okay. And as it is going to roll, the initial potential energy will be converted into the kinetic energy, and kinetic energy we know is of two types, translational as well as rotational kinetic energy. So therefore we can say that when the cylinder is at rest on the edge, at this position, the potential energy will be maximum. Potential energy is maximum, and kinetic energy is 0. Okay, so this is basically the representation of figure A. Let this be figure A, this be figure B, and let us suppose this is figure C. In the next part, you can say as the cylinder rolls, it starts to roll. As the cylinder rolls, the potential energy is converted into the kinetic energy. You can say potential energy is converted into kinetic energy, which will be our translational, which is also called as a linear, and plus rotational. Okay. And this can be with respect to figure B as well as figure C. So therefore, we can use principle of conservation of energy you can say potential energy initial plus kinetic energy initial is equal to potential energy final plus kinetic energy final. And initial kinetic energy is 0, as we all said, because the cylinder is in rest. Kinetic energy initial is equal to 0, and potential energy is due to, or we can say because of we are calculating the potential energy basically at the center of mass. So potential energy is at center of mass, which is at a height r from the fixed block, Therefore, we can say potential energy initial is equal to mgr. Now we say that cylinder is rotating through angle of theta. You can say that when cylinder rotates through angle theta, the center of mass is going to drop by a height r cos theta. Okay, because previously the height of center of mass was this one. Okay, now the center of mass is going to drop by a height of r cos theta. Let me draw this. It is not giving a correct picture. So initially this was our center of mass, and now it rotates by angle of theta. So this is our theta, okay, and this is the so when the cylinder rotates about the angle theta. So let me draw it again. So this was the initial position of the cylinder, and this was our R. Now cylinder rotates by angle of theta, so the center of mass will be traveling like this, and suppose this is our R and this is angle theta, so you can say this height will be coming as R cos of theta with respect to the horizontal. Okay. So therefore you can say that when the cylinder rotates about the angle of theta, so this is angle rotated with respect to the cylinder, and so this will be coming as R cos of theta. So we can write it as the center of mass descends to a height of R cos theta. And this is with respect to the horizontal. So therefore we can say the final potential energy final will be equal to mg, and we have R cos of theta. Next we are going to find out the kinetic energy, which is the translational as well as rotational. Kinetic energy final has two components. Rotational kinetic energy, which will be our half moment of inertia omega square, and we have translational kinetic energy, which will be equal to half m v square. And for a solid cylinder, the moment of inertia we already know. You can say for solid cylinder, moment of inertia I is equal to half m r square, and it is said that it is rolling without slipping. So you can say for rolling without slipping, omega is equal to v upon r. Okay, let me make a correction here. This figure, this is not theta. Okay, theta will be with respect to this figure, okay, with the vertical. This will be theta. Okay. So therefore you can find out that final kinetic energy final will be equal to summation of both, that is we have half mp square plus half I omega square, substituting value of I as well as omega, we get this as half omega square plus 1 by 2 m r square, and we have here v square upon r square. R square and r square cancels out, and we are left with kinetic energy final will be equal to 1 by 2 mv square plus 1 by 4 mv square, and this will be coming as 3 by 4 mv square. And to the conservation of law, let us call this as equation number 1. So using equation 1, we get mgr is equal to mgr cos theta plus 3 by 4 mv square. Mass we can cancel out throughout, so we are left with v square is equal to 4 by 3 g r1 minus cos of theta. Let us call this equation number 2. Next is velocity of center of mass when the cylinder is about to leave the contact with the edge. Velocity of center of mass at the point of leaving. And at the point of leaving, when it's about to leave the edge, the contact force that will be acting will be equal to 0. And contact force is our normal force, so value of that normal force will be equal to 0. You can say at the point of leaving, the contact force, that is normal force, will be equal to 0, and the required centrifugal force will provide the centripetal force, so as it remains in the balance. So therefore the centrifugal force which will be given as mv square upon r provides the required centripetal force. For the necessary balance. Therefore, we can just draw the figure. So at this point it is about to leave, so we are going to have mg in the downward direction and two components. This will be our mg sine of theta, and this will be our mg cos of theta, and here the normal value will be equal to 0. So at this angle it says that theta is equal to theta c. So you can say at theta is equal to theta c, mg cos theta c will be equal to mv square upon r. mass cancels out, and using the equation number 2, from equation 2 we get four by 3 GR, and this is 1 minus cos of theta c divided by R is equal to G cos of theta c. Okay, simply substitute the value of V square from equation number 2, and R goes with R and G cancel out with G. So we can write this expression as 4 by 3 minus 4 by 3 cos of theta c will be equal to cos of theta c, and this can be written as 4 by 3 is equal to cos of theta c as common, so this will be 1 plus 4 by 3, and we get 4 by 3 is equal to cos of theta c, and this becomes as 7 by 3. 3 cancel out by 3, so we get cos of theta c will be equal to 4 by 7, and theta c will be equal to cos inverse of, theta c will be equal to cos inverse of 4 by 7. And next we find out value of the velocity, once again using equation number 2, because we found out what will be our cos of theta c. So you can say from equation 2, V square is equal to 4 by 3 GR, and we have here 1 minus cos of theta c, which we already found out. Substituting the value, we get V square is equal to 4 by 3 GR 1 minus 4 by 7, and this comes as 4 by 3 GR, so this will be 3 by 7. 3 cancel out with 3, so we get velocity is equal to 4 by 7 GR and its square root. So we found out the velocity of the center of mass, as well as we found out the theta c when it is about to leave the angle, when the cylinder is about to leave the your block. The last part, we are supposed to find out ratio of translational to rotational kinetic energy. Ratio of translational to rotational kinetic energy. So rotational kinetic energy we can easily calculate. Rotational kinetic energy, let us suppose that KER will be equal to 1 by 4 m, and this is our V square, that is 4 by 7 GR. So we get kinetic energy rotational will be equal to 4 cancel out with 4, 1 by 7, we have this mgr. Now it is said that when the center of mass is in the horizontal line of the edge, okay, so which basically means initially the cylinder was right at the edge, and this was, let us suppose, the center of mass, and now the cylinder is about a position when its center of mass is at the horizontal. So at this position, the entire energy was your potential energy, whereas at this position, the energy will be the summation of kinetic energy rotational plus kinetic energy translational. Okay. So conservation of energy, which we have already used, the same formula, we can say potential energy is equal to kinetic energy rotational plus kinetic energy translational. Rotational we already found out, potential energy we know, here it is R, so this will be mgr. Kinetic rotational is 1 by 7 mgr plus kinetic energy translational, and this will be giving us kinetic energy translational will be equal to mgr is common, so this will be 1 minus 1 upon 7, and this comes as kinetic energy translational is equal to mgr, and this is 6 upon 7. So we have to find out the ratio. So kinetic energy translational oblique kinetic energy rotational, so we get this as mgr 6 by 7, and we have 1 by 7 mgr. mgr and 7 cancel out, this comes as equal to 6. So the ratio is 6:1. Okay. So this completes the question. Thank you.